Done. Hello?
Yes.
Yes.
Little more above also, that mic.
Again?
Yes, yes. That mic you can keep.
Higher.
Higher.
Here? Okay. Okay.
This board and this one, right?
Yeah, I think maybe here, this one, because easy for me to walk. Ah, is it okay? Because I'm afraid
You can
I,
come up to this.
yes.
You can keep little things towards you. You can come up to that.
Yeah, sure.
So on behalf of the organizing committee of this GIAN program on dynamical system and trial theory, IoT and cryptographic applications, you all would have attended the past 5 lectures by Professor Lamberto and 2 tutorials. Now, Dr. Noor Aisa Patel from University, National Defense University of Malaysia will handle the classes for the next 4 lecture hours and 2 tutorial hours will be handled by Dr. Noor Aisa Patel. His expertise is IoT and cryptography applications. She has vast knowledge in modeling, signal processing, and secured image communication. So these are nowadays very important because there are a lot of hacking and many things and digital frauds and many things are happening. So how one can predict, not prevent themselves when sharing very important information and other things. Without any further delay, I welcome Dr. Noor Aisa Patel to this GIAN course.
Yeah, thank
And
you.
the podium is yours.
Yeah, thank you. Thank you. Thank you, Professor Silverrush. Okay, so, yeah, as mentioned, you can call me Aisha. It's actually Fataf is actually my father's name. So in Malaysia, we use our father's name as the initial. So my exact name is Aisha. Okay. Okay. So I'm writing here is lecture 1 because it's a lecture 1 for me. So basically, it's a lecture 6 for you guys. Okay. And my lecture today for this 1 hour is a basic understanding of chaos. Professor Lamberto already mentioned a lot of times about chaos. So today I'm going to briefly explain what is chaos for your understanding. Okay, and just want to mention, I'm wearing the same scarf here. I didn't plan it. Today, when I will check my slides. Oh, I'm wearing the same scarf with the pictures given. Okay, so yeah, that one is different. That one is green color actually. I suppose I have to give the same, right? Okay, so before we start, I would like to introduce my university. I love to introduce my university because in Malaysia we are a unique university. So in Malay we call it as University Pertahanan Nasional Malaysia, and in English we call it National Defence University of Malaysia. So there is a defence in there, meaning that actually we are teaching a soldier, a future soldier. We are teaching future soldier. We call it cadet. So you can see I have few students in cadet and now already become officers. In fact, might be a major now and higher salary than me because they got so many allowance there. So yeah, university, I mean UPNM, we call it as UPNM. In fact, giving a salary to the students, to the cadets, to learn. In fact, the fee is also free for them. They are giving, not allowance, sorry. They are giving a salary, okay? A salary, and also they included the allowance also for the student. So when we are talking, I mean, our staff talking about the bonus, they also will talk about the bonus because they are given as same as the government officer. Even they are doing students in particular in university. So that is good for them, but then I think maybe the best part for that is they have to undergo physical training, marching, they have to tolerate with so many people in, you know how military act is, so that is what they have to pay for it. So basically during morning 8 to 4, they will go for the classes, and after that they will go for the training. Okay, the training is supposed to be up to 10 because after 10 they will set light off. But knowing military, there will be like no turning off lights. But yeah, we actually as faculty members didn't involve with that. So maybe sometimes we have to hear, ma'am, I cannot do this assignment. My officer asked this, and this. So I sleep at 5. So I have no time to do my assignments. There is always the, you know, the reason, I mean the excuses they are giving to us. But then yeah, as a staff, I mean as a lecturer, we have to be more strict, and if not, they will not listen to us. If you are, oh, it's okay, you take the time. No, we cannot answer that way. So whenever we set the due date, so they have to do the due date. So basically, what they will do is like copy paste. So that is actually the best of military cadets. But then they are actually very clever. If we can compare with the civilian, actually we also have a civilian nowadays. But even they are always copy paste the assignment whatsoever. But then their exam, actually they are perform well. So that is the best part of the cadets. In fact, nowadays our government's changing a bit. So the student more likely to have, we more likely to have the civilian rather than the cadets now. Maybe because we produces graduates cadet every year, so the military officers is already increasing, so the needed is less now. So that's why we only maybe about 30% of the students is the cadet, and another 70 is the civilian. So if you can see in this figure, a lot of cadets. This is my previous long before, maybe 10 years before. So currently, I would have about 5 cadets out of 30 students. So in my class currently this semester. So it reduces. So, and I'm happy because I don't get so much damn reason and excuses from them. Sometimes they are not coming also. Ma'am, my officer is calling. So many excuses you can hear from the cadets. And cadets love to give the excuse. Okay, but then yeah, they are clever. Okay, so that's all from my university, UPNM. I just want to make you guys remember me, so you can remember my university. Okay, so this is the outlines that we go. It just actually for today, for this 1 hour lecture is very simple. Just the introduction of chaos theory and the nonlinear system. So we go for introduction to chaos theory. So what is this chaos theory is all about? Okay, so it's actually chaos theory is developed by mathematician, which is they observe certain system do not behave as traditionally we expected. Like for example, if we have linear equation, whenever you put it input, you will get the output. So you'll be proportionally behavior between these two. So for this chaos theory is actually they do not behave traditionally as what we expected. So it's actually we get unpredictable. So chaos theory we always comes to unpredictable system where we encounter this system to be unexpected and a very incomplex behavior. And classical tools of calculus actually is not inadequate to understand this system. So this inadequacy comes to the new field of chaos theory. Okay? And actually, chaos theory is a deterministic nature because it's governed by a rules. We are giving them a rules, but then they exhibit random behavior. Okay, they exhibit random behavior and unpredictable. So meaning that there are fixed equation. There are fixed equation for the system that govern the system. However, they often display as a random and unpredictable. So this randomness where the magic is lies. You know, because you are like to be structured, but then you are not structured at all. Okay, so that what we call magic of chaos theory. Okay, so the core concept of chaos theory, there are four that I list here. The first is, as I mentioned, is dynamical system. So when we talk about dynamical system, we should have the equation. So, and the equation for dynamical system, when we talk about chaos, would be nonlinear dynamical equation. And we can have few examples of the system, like pendulum for physical system. Biological system, we can talk about population dynamic. So this is the example. Economic system, stock market fluctuation. So there are many more, actually, there are many more. In fact, nowadays, when we have the COVID-19 and so much of the virus infection, right? So we can model the system, and that system will predict will be in chaos. So means that we cannot predict the behavior, and it will be exponentially growth, as you can see in COVID-19. Okay, and I just mentioned just now nonlinear. So the chaos should be nonlinear. So the output is actually not proportionally to the input, whereby like we have like as I mentioned just now, is a very simple equation. If you have y equal to 2x, if you put x equal to 1, the y will be directly for the y equal to 2. So it's a direct proportional. So now for the nonlinear system, it will be not directly proportional. So means that there will be a loop. Okay, we develop a feedback loop where small changes can be amplified or suppressed. So means that the loop will make the system amplified. It will be maybe a bigger, or it will be suppressed. Okay, so that's why we will make the system complex and unpredictable. And just now also I mentioned deterministic system, because it's governed by a equation. There is some rules that govern the system. So actually it can be predicted in the short time, but we cannot predict in the long time, because in practice the small error will grow exponentially. So we cannot even predict in the long run. Okay, and lastly is randomness. So it is the system is exhibit behavior as a random, but then it's root as the deterministic system. So this all is a core concept of the chaos theory. Okay. So to define chaos theory is actually a branch of mathematics that study complex system, whereby the behavior is highly sensitivity in initial condition. I make it short as an initial condition. So this is what we call it deterministic chaos. Okay, and Okay, so what does we mean by sensitivity to initial condition? So it means that if we put a small difference, or maybe we would say insignificant difference of the initial condition, but then the output will be very different from the initial what we expected. So means that tiny changes in our initial condition will give us a different result of the output. Okay, and then it's also the same as I mentioned. Actually, what made this system fascinating is that they evolve over time. So they evolve over time. They are following the specific rule. There are specific rules that they are following, but then the outcome appeared very random and unpredictable. So even, for example, if you want to check the weather, the temperature is reading like 30, for example, but then we put it in our system as 30, but then the real temperature is actually 30.1. Okay, so the reading from the temperature is 30, yeah, but then you know the reading of our tools might be have some error. So in actual temperature, surrounding is actually 30.1. So it's just a difference of 0.1. But then the prediction comes later will be very, very different in these two cases. Even it's just a very slight difference of 0.1. So that is what chaos theory is about. Okay, and I will explain the key characteristic, which is deterministic yet unpredictable. Okay, so it's actually the system governed by a set of rules, but then the outcome is unpredictable over time due to exponential sensitivity to initial condition. Okay, we can see the example as the double pendulum here. Is it I can run? Okay, I can run again. So double pendulum, you can see the initial is actually almost the same, but then when it comes evolve over time, the result is actually very diverge from each other. So that is what I mentioned, the sensitivity of the initial condition and nonlinearity and complexity. Okay, so this is the source of chaotic behavior. So small changes in the part of the system can have disproportionate effects on the whole system. Okay, so actually mathematically nonlinear can be expressed as like product term, trigo, exponential, a power of variables. So in the system, if you have this term, this nonlinear term, for example, the product rules, the powers variables, exponential, trigo, so this system will make our system chaotic. Okay, so my question to you, have anyone ever observed any system in daily life where a small initial change lead to a big or unexpected outcome? Okay, means that anything that you have observed in your daily life, in where the small changes actually will lead to unexpected outcome. Come again? Compounded? Compounded iteration. Oh, interest. So as I mentioned just now, you mean is a financial stock market. Yes, that will be correct. So fluctuation in the stock market is also unpredictable. So yet, even there is a tiny difference or tiny what we call announcement will be very affected the system. That is very good example. I will share you one. I don't know. It's happened to me every day, because whenever I go to my university, I use a car. So it happened to me whereby a traffic jam. And surprisingly, I encountered a jam, traffic jam. The road is very congested. But then when I go through, nothing there. There is nothing. There is no accident. There is no stopping car. But then, what is a traffic jam towards the end. So it's nothing. But then, traffic jam is occurred. So why do you think that is happening? So I will share you one video. I would say this is interesting to explain why a traffic jam is occurred.
You're cruising down the highway when all of a sudden endless rows of brake lights appear ahead. There's no accident, no stoplight, no change in speed limit or narrowing of the road. So why the is there so much traffic? When traffic comes to a near standstill for no apparent reason, it's called a phantom traffic jam. A phantom traffic jam is an emergent phenomenon whose behavior takes on a life of its own, greater than the sum of its parts. But in spite of this, we can actually model these jams, even understand the principles that shape them, and we're closer than you might think to preventing this kind of traffic in the future. For a phantom traffic jam to form, there must be a lot of cars on the road. That doesn't mean there are necessarily too many cars to pass through a stretch of roadway smoothly, at least not if every driver maintains the same consistent speed and spacing from other drivers. In this dense but flowing traffic, it only takes a minor disturbance to set off the chain of events that causes a traffic jam. Say one driver brakes slightly. Each successive driver then brakes a little more strongly, creating a wave of brake lights that propagates backward through the cars on the road. These stop-and-go waves can travel along a highway for miles. With a low density of cars on the road, traffic flows smoothly because small disturbances like individual cars changing lanes or slowing down at a curve are absorbed by other drivers' adjustments. But once the number of cars on the road exceeds a critical density, generally when cars are spaced less than 35 meters apart, the system's behavior changes dramatically. It begins to display dynamic instability, meaning small disturbances are amplified. Dynamic instability isn't unique to phantom traffic jams. It's also responsible for raindrops, sand dunes, cloud patterns, and more. The instability is a positive feedback loop. Above the critical density, any additional vehicle reduces the number of cars per second passing through a given point on the road. This, in turn, means it takes longer for a local pileup to move out of a section of the road, increasing vehicle density even more, which eventually adds up to stop-and-go traffic. Drivers tend not to realize they need to brake far in advance of a traffic jam, which means they end up having to brake harder to avoid a collision. This strengthens the wave of braking from vehicle to vehicle. What's more, drivers tend to accelerate too rapidly out of a slowdown, meaning they try to drive faster than the average flow of traffic downstream of them. Then they have to brake again, eventually producing another feedback loop that causes more stop-and-go traffic. In both cases, drivers make traffic worse simply because they don't have a good sense of the conditions ahead of them. Self-driving cars equipped with data on traffic conditions ahead from connected vehicles or roadway sensors might be able to counteract phantom traffic in real time. These vehicles would maintain a uniform speed, safety permitting, that matches the average speed of the overall flow, preventing traffic waves from forming. In situations where there's already a traffic wave, the automated vehicle would be able to anticipate it, braking sooner and more gradually than a human driver, and reducing the strength of the wave. And it wouldn't take that many self-driving cars. In a recent experiment, one autonomous vehicle for every 20 human drivers was enough to dampen and prevent traffic waves. Traffic jams are not only a daily annoyance, they're a major cause of fatalities, wasted resources, and planet-threatening pollution. But new technology may help reduce these patterns, rendering our roads safer, our daily commutes more efficient, and our air cleaner. And the next time you're stuck in traffic, it may help to remember that other drivers aren't necessarily driving spitefully, but are simply unaware of road conditions ahead, and drive accordingly. In a hurry but love physics? We've got a book rec for you.
Okay, so you see the traffic jam, because one car brakes, the other at the back behind it have to brake, the other at the back also have to brake. So this erratic actually causing a ripple effect. So this ripple effect is actually giving us the chaos. So during the traffic jam is actually chaos. So that is what I encounter every day of my life, when I want to go to the work, especially. And actually also during a holiday session. Nowadays during holiday everyone's coming out. In Malaysia we are lazy to cook, so everyone going out for eating. So during holiday the worst traffic jam would be occurred in Malaysia. So that is just for your knowledge. If you are coming to Malaysia, don't be surprised with the traffic jam. Even that is, I'm talking about highway now. I didn't talking about the federal roads or any road. It's a highway. So and that highway is actually we are paying for the toll. Each about maybe 10 kilometers or 20 kilometers, there is a toll I have to pay, but then it's a jam. So it's just because of this time and these things, and the more cars coming, right? So this is what chaos. Okay, so let's go to the application. So this is example of the application of chaos theory. So we have a weather forecasting. In weather forecasting, even we can predict in a short period. We cannot predict in the long time. So because of this unpredictable, okay, and even if there is any tiny error, we input it in the system, it will be very vastly different in the outcomes. Okay, so the weather forecasting, even a best weather forecasting also, we cannot have a long period of forecast. And in engineering and physics, actually chaos describe the turbulent flow in the fluid mechanics, and engineers use chaos theory in vibration control to ensure stability and reliability in mechanical structure. I will explain in deeper towards the end of my lecture about this. And also we have biology and ecology. We model the population, dynamics and ecosystem. Like for example, we have the system is about food supply, how many species are there. So it's all actually in chaos, because if you put it, I mean, if the species is more, I mean, we have the stable equation, we have the stable population in a time, but then when the species double, so the food chain, the food supply will be limited. So that in that particular time, the process will be very chaos, because you have so many species, so many population, but then your food supply is limited. Okay, so it's also, we can model through chaos. And last but not least, this is just an example of mine. We have cryptography and security. So yes, cryptography is also one of the application that we can use, because of this randomness of chaos, whereby we can use the solution of chaos to use in cryptography as a key, and in fact to do the encryption algorithm. So because of the randomness of the solution of the chaos. So it's very difficult. It's very difficult to for cryptanalysis to what we call to predict our algorithm, because I need to work this, right? I forgot. But then you can hear me, right? How about the recording? Okay, so yes, I'm using cryptography a lot towards my research for in chaos theory. So yeah, it's good. It's good because we have the system, we have the equation, and based on the equation, we can use the result to use for the key to design our algorithm, and we can see the system whereby the prediction our cryptanalysis is very difficult to go. Okay, so now I would like to talk about nonlinear system. So we need to have this root because nonlinear will give a result of chaos. Okay, so nonlinear is referred to a system which the change of the output is not directly proportional to the change of the input. Okay, so unlike the linear system, small changes in the input is proportionally changes in the output. So I'm giving you the example here. As just now I mentioned y equal to 2x. So basically, if you go to the engineering, we have the Ohm's law, V equal to I R. So if you double the current, so the voltage across the resistor is also double. So that is very what we call simple and linear. So chaos is not that way. So it is involving non-linear, whereby, as I mentioned, the linear can be powers, can be product of variables, trigo, or exponential function. Okay, so that would be whenever you want to design a system, this non-linear term should be there. Okay, and the small changes in the output can lead to this proportionally large effect in the output, making the prediction will be much harder. Okay, so one of the example of chaos theory is logistic maps. So logistic map is actually we model the population dynamic. Okay, so small changes in the growth rate can lead to completely different behavior in population growth, ranging from stable to chaotic patterns. So basically, in chaos, we observe the stability. So we need to check the behavior where it starts from the stable and it moves to chaos. Okay, so this nonlinear gives the sensitivity and the amplification, which is we call it as sensitivity dependence on initial condition. Okay, so now we take a look of the example. Okay, logistic map. So logistic map is governed by this equation, whereby the successive solution is according to the previous solution, and R is defined by growth parameter, and X is population, where we normalize from the range 0 to 1. Okay, at a certain behavior, at a certain value of R, this system will show a simple behavior whereby the point will be in the stable, we say converge. But then as we increase R, the system will be very chaos, where it demonstrates a period doubling oscillation, and at some points, the system will generate complex and unpredictable outcome, whereby we call it as chaos. So after this, we go in deep for this logistic map. Okay, so as I mentioned, double pendulum. So it's actually mechanical system. It's attached. One pendulum is attached to the end of the other one, and it consists of two rotating arm with its own mass and length. So in double pendulum, they involve a trigo. So this trigo will make the system non-linear. And if we have a small changes in angle or velocities, we will lead drastically different motion paths over time as the energy is transferred between the two arms. The system has a bit chaotic motion. Okay, so usually we often use double pendulum to study the chaotic behavior in the physics. So it's about energy. So usually when we talk about energy, we use double pendulum. Okay, even minor differences in starting point will be result in significantly different output. Okay. Now we move to the nonlinearity, where this nonlinearity will lead to chaos. So there are three things, aspect that we have to check: the feedback loop and the amplification, bifurcation, whereby it's the transition of the chaos, and also the unpredictable in nonlinear system, whereby we check the sensitivity analysis. Okay, so as I mentioned just now, nonlinear will produce feedback loop where the output affect the input. So it will lead the cycle we call isolation that can amplify the effect. Okay, so for example, as I mentioned, logistic map, the population generation affect the next generation. So if the population is too high, it will be reduce resources. So it will be lowering the next generation size. Okay, so this feedback will be create the oscillation, and at some growth rate it will be chaos. Okay. Also, we need to check the bifurcation, whereby bifurcation is very important. We need to check the transition of the chaos. So for the bifurcation, we need to check the parameter that what we call that will be affected or effect that will be affect the system. So it may be undergoes bifurcation, where point the system changes drastically. So bifurcation is actually the changes of the behavior, and towards the chaos, the behavior will change drastically. Okay, so if you have double period bifurcation, we call it the behavior is moving from stable to oscillation, or maybe double oscillation. But then if parameter continue to change, this doubling process happen repeatedly, so the system will become more complex, and this is whereby chaos come in. The system will not be predicted anymore. And unpredictability in nonlinear system. So this is where initial condition are very important, and this system governed by the set of rule. It will be they can be unpredictable because of this sensitivity of initial condition. Okay, so small changes or uncertainties in initial can amplify rapidly. Then we can the long-term prediction is impossible. Okay, and how the way we measure unpredictability or sensitivity depends on initial condition using Lyapunov exponent. sorry, my mistake. This is Y, Lyapunov exponent. Okay, so in Lyapunov exponent, we can see whether the system is in chaos or not. So in this slide, there are two major things in chaos theory, whereby bifurcation and also Lyapunov exponent. Okay, so Lyapunov exponent give us the knowledge of the sensitivity of initial condition. So this is a key aspect on how we need to understand non-linearity, whereby it leads to chaos. Okay, so I would talk about the butterfly effects. So this butterfly effect is actually metaphor from Lorentz. So Edward Lorentz is one of the mathematician that we can say that he is the one who discovered chaos. So actually what is happening during his time, he's actually want to predict weather. He's doing the weather prediction model. So from he modified and simplified one model. He simplified one model. This is happened in 1963. Okay, so in that model, I would say he has this model and it's already simplified. I will give you the model after this, whereby in first he want to run it because he doing the weather prediction. So he run it, the weather prediction. He's using the initial condition of 0.506127. So this is the full precise value for the prediction that time, 0.506127. So there are 6 significant figures. Okay, so after he ran that simulation, he got the output of 2 months of prediction. Okay, and then all of a sudden he want to try another value of initial condition. So he just put, rather than 6 decimal places, so he just put 0.506. So he just take the first 3 decimal places, and then he go for a cup of coffee. After 1 hour, he come back and he got the result, the prediction, also for 2 months. And when he look at the result and he compared the result, he thought his laptop has a problem because the result is not the same. So, but then when he checked one line by line of the prediction, so at first the prediction almost the same, and then towards the next 1 decimal letters, 1 decimal missing, and another decimal missing, and then the decimal missing, and towards the end, totally different output coming from the second one. So during that time, he realized that because of, I would say, when you go for the YouTube, you will say the word culprit is there. I mean, it's not a culprit, but then the initial condition, the second initial condition is actually the reason why the different result is coming. So that's why I mentioned even insignificant figures actually are giving us very vastly different output in this when we are talking about chaos system. Okay, so this is what I mentioned. So even tiny changes in the starting values of his weather simulate in and lead to vastly different outcomes, where this is showing the complex system could be highly sensitive to initial condition. Okay, and this sensitivity made the long-term prediction difficult. Even actually our system is a deterministic equation. So his findings fundamentally challenge that the belief of deterministic system, like weather, could be accurately predicted given the precise initial data. Okay, so this is actually just a metaphor, the butterfly effects. It didn't measure anything. So when you are talking about butterfly effect, it's just a metaphor. Okay, so the correct term should be sensitivity dependence of initial condition. So during his lecture, if I'm not mistaken, in 1963, he used this metaphor whereby the butterfly flapping in the wings in Brazil actually can cause a tornado in Texas. So it's a two different continent, but then because of the butterfly flapping in Brazil, the tornado will cause in Texas. So this is the metaphor that he used. Okay. So actually, why bother with butterfly effect? So we just want to mention that butterfly effect is actually captures the essence of chaos. So and then butterfly effect will limit the predictability, and even we know the governing rules perfectly, but we cannot completely control the outcome because of this sensitivity. Okay, so this system feature will diverge with a very tiny difference. So that is what we call a butterfly effect. Okay, so in real world example, we already discussed actually all these things. It's actually the butterfly effect give an intuitive gateway into chaos theory to set up for the mathematical rigor in the next section. Okay, so after this we go to the mathematical rigor for this butterfly effects, which is we call it as sensitivity dependence on the initial condition. So we just want to see how tiny difference of initial condition would lead to very vast different outcomes. Okay, for example, if you have a tiny variation in the air pressure, so initially the significance the initially significant we can alter the wind pattern whereby it will be shift weather condition thousands of miles away. Okay, and in financial market, as our friends just now giving the example, a slight change in the interest rate will cascade or affecting investor confidence or stock market worldwide. So prediction of the financial stock market is quite difficult. I mean, in the long run. And also for biological system, I'm giving example here, a tiny increase in temperature. So it's just a temperature difference, but then it will be slightly alter the insect production rate, okay, reproduction rate, okay, because the temperature, sometimes the higher temperature will lead the increases of reproduction rate, so leading to for more food for the certain bird, okay. So which is the impact the predator higher up for the food chain. So everything has the consequences. So that's why in many biological system that we can use to model, so we can see we can see how the behavior of the system happen. Okay, so now this is the mathematical rigor of the chaos theory, sensitivity dependence on initial condition. So what does it mean? It means a tiny difference in the starting condition would lead to exponentially diverging outcomes. So these properties actually will make the system, the chaotic system unpredictable. So we use Lyapunov exponent to calculate or to measure. And how we relate to chaos theory? Because sensitivity dependence is actually a central of chaos theory because it introduces unpredictability in deterministic system where it governed by a fixed rule. So even we know the exact governing equation, because of this exponential divergence, we cannot predict the system. Okay, so I want to talk about the Lyapunov exponent because it measured the sensitivity dependence of the initial condition. So Lyapunov exponent, they measure how fast the trajectories path diverge or converge from each other. So you need to imagine you have two tiny difference of initial condition. So we want to see how it diverge or how it converge. Okay, so it quantifies the rate at which two points that start very close to each other. So we want to see whether it come closer or move further from the system as the time evolve. Okay, so basically we use this equation to calculate to measure the Lyapunov exponent, and the result would be either the Lyapunov exponent is positive or negative or zero. There will be three possibilities. If the Lyapunov exponent is positive, we would say the trajectories or the behavior of the system is diverge, and hence we can say that the system is chaos. Okay, whereby if the Lyapunov exponent is negative, the system trajectories is converged to one point, and we would say the system is stable or dissipative. And what about we have zero? If the Lyapunov exponent zero is actually, we can say the constant distance is maintained. I mean, it will be the same because zero. Because when we talk about Lyapunov exponent, we check the difference between 2 points. Okay, so if there is zero, there is no distance at all. So the system behavior would say the quasi-period or marginally stable. So that is what we will have for the Lyapunov exponent. Later on also we will go for the MATLAB, how to find the Lyapunov exponent. Okay, so how long I have actually? What time your lunch hour break? Oh, it's almost 2 minutes more. Okay, so we check this time series. This is time series whereby I have three initial condition here. As you can see, it's very insignificant difference from each other. But then, as you can see, towards the time evolve is basically about the same. Towards the end, it's diverging. I mean, the trajectories is not the same at all after the time evolve. So this is what we call sensitivity of dependence of the initial condition. So we will do this later, so you can see. You will see actually the time series fluctuate in the not the same manner. Okay. And also this is the graphical representation of phase. Okay, so I'm giving you the same, I mean slightly difference of initial condition from here, but then as you can see the trajectory between these 2 points will be very different. Okay, so but then it's still confined like the same pictures, right? Why that is happening? Even the result is different, but then it's still confined in the same pictures. I mean, in the same butterfly. I say this one is butterfly because this is what Lawrence found. So it's still even you can see the difference, but then the pattern would be like butterfly. So this is why, because chaos also we will say bounded. Okay, so boundedness is also important. The trajectories will not going far. It will be bounded in the same manner. Okay, so Okay, so this is practical application of sensitivity dependence. I'm giving you in two. One is in the engineering and one is for the prediction. So this is the challenge actually for the engineers and for prediction to do and to have to do something. So for example, in aircraft stability, okay, we have a few parameter, I would say few state variables that is important, like airflow, weight, and control input. So you need to make sure the flight is stable. So if there is a turbulence happen, so means when you have the turbulence, means chaotic is there. So how you want to manage the aeroplane? So that is why chaotic very important for engineers to check the system when the system is chaos, so they can have the control input to their system. Okay, so for example, we have the autopilot system. In aircraft, we have autopilot system. So this autopilot system will make continuous adjustment to keep the aircraft level and on course. So this autopilot actually developed after we check the chaos behavior. Okay, so this is very important. So financial also we have, I'm giving here the parameters or the variables that is very important, whereby it leads to the chaos. So with different error, our initial condition will lead to different forecasting. So so this is what example that I can give to show why chaos theory is important and why this is challenge for the engineers and also for the prediction to do. Okay, and lastly, I would like to emphasize the difference between butterfly effect and sensitivity on initial condition. So butterfly effects is actually just a metaphor, and sensitivity on initial condition is actually the what we call the mathematical properties of chaos, whereby we measured by Lyapunov exponent. Okay, I want to show this one, but I have no time. I don't know. Well, I'm not enough. Okay, so logistic map. This is actually one of the example. We will say road to chaos. Okay, I will make it in fast because we have time. Okay, so when you have this one example of R equal to 2, so we have the stable equilibrium, which means the point stable to one point. Okay, and then when it moves to R equal to 3.1, we have the simple oscillation. As you can see, the system doubling. Okay, oscillation. Towards to 3.5 or 3.55, the complex oscillation occurred. So in this one, it's still not chaos, but then the doubling of oscillation to 4 to 8 to 16 to 32 and so on. And when you change your R to 3.57, the system fully chaotic. So in this state, the population values no longer settle into a repeating cycle. So there will be no repeating, there will be no oscillation after the chaos behavior. Okay, so this is the example. I don't know if you can see this one. I think it's very nice. It's very nice. So from the start 0.1, it's converged to 1 point, and then it moved to when A is R to 2, A equal to 3, A equal to 2.1. How many stable points there are moving? And this is the oscillation happening to 3.1. So maybe 8 here. The oscillation is 3.2, maybe 16. The oscillation happened 3.5, maybe 16. You see the moving. And 3.55, maybe 16 oscillation happening there. And now if you move towards to 3.7, it will be root to chaos. So that is the hallmark of chaos. Okay? And this is Hanon map. So in Hanon map, maybe it will be the same. I mean, if you have, okay, this is the equation of the Hanon map. So I'm doing it fast. So A is giving the system, is affect the system. So if you can see here, I'm changing the value of A from A equal to 1, A equal to 1.2. You can see the behavior of the system is different for each value of parameter. So towards when A equal to 1, we have the stable behavior. When we have A equal to 3, we can say bifurcation almost happening. I mean, chaos is almost happening. And when we have A equal to 1.4, the chaotic behavior is there. So, and this is what we call the strange attractor, whereby it is bounded, non-periodic, and it is very sensitive to initial condition. Okay, this is what I mentioned. I want to show you Lorentz system. So this is Lorentz. So this is the equation of Lorentz. We will go deeper to after this. So in this system, X is represent the convection current, Y is represent the temperature variation, and Z is represent the vertical. So Y is horizontal, Z is vertical temperature. Okay, and sigma, rho, and beta is also represent something. And there are two nonlinear terms here, whereby you have X, Z. It's just a product, right? It's just a product of variable X, Z, and XY. There are only two nonlinear, but then this nonlinear makes the equation something happen. I mean something else. Okay. And I'm showing you here also the different type of behavior when we change the row. Okay. At row 5, you have stable, converge to a fixed point. And then we have row 15, whereby the oscillation it started to begin, predict behavior. And when we have row 28, we have the chaotic behavior. So actually, I thought I have time, so I want to go deep for each, but then I just touching. So hopefully you can try to understand. And we will go for later. Okay, so this is the application. Also, I have been talk about it in just a few slides just now. So this one, we managing chaos in vibration control and chaos cryptography. So we are using the sequence of the solution for the key and also for to design an algorithm. And also predictive modeling. I also touched the prediction, whereby we cannot predict in the long run. We can have in the short term only. And for sure, we have to use the competition technique for this type of equation. And to expand chaos theory, so we have machine learning and AI, quantum chaos, and chaos in neuroscience. So basically, in this key 1 and key 2 is my future direction. So I will go for this, and there are few questions to raise how we want to highlight chaos in this field, ML, AI, and also quantum. Because nowadays, I would say maybe 10 years after this, we will have the quantum crypto, whereby our current crypto cannot survive already, because in a second, our secure data will be just being exposed by this quantum. So that will be my future direction. Okay, so as a conclusion, so we already explored the foundation concept, the deterministic, the non-linearity, and the butterfly effect. And we already see the changes on the initial condition will lead to very drastic different outcome. And I'm giving you a few examples just now. It's actually a very simple one, but then it produces a complex and unpredictable behavior, but with a governed governed by a set of rules. And also I'm touching about the real world application in variation control, chaos theory, and also predictive learning. So it's quite faster because we don't have a time, but then I will go deep for the next session for chaos, especially for Lorentz and Rosler. So after this, we go deeper into the dynamical of chaos, Lorentz and Rosler. Okay, so with that, thank you. I'm giving my phone number and also email. You can email me if you have any question, or you can text me if you have any inquiries to ask. Okay, so with that, thank you. We meet again after this. Sorry, taking you 13 minutes.